Welcome to Math151 Computing Derivatives. What we're going to do with this lesson is use the definition that we've worked on this week of how to compute a derivative at a point or for the whole function using the limit definition, and we'll review that first, and we'll use that to simplify our work in a couple of important special cases. So first, remember the definition of the derivative at a point, the rate of change of a function with respect to x, or if it's on a curve defined by y equals f of x, that is, we plug in an x and get a y value to get the points on the curve. Then we define the following. F prime of x, the derivative of f of x with respect to x, is defined to be the limit as h goes to 0 of f of x plus h minus f of x divided by h. Well, what does this represent? This is precisely the limit taken on the slope of the secant line between the points at x and x plus h. Notice the example here. So if my x point would be about negative 2.5, and my h is the distance between this point and the next one, I can move that out further or shrink it, and I can move my point anywhere in the curve I like. Let's set my x value to negative 2 and my h to 1. That's an easy to 2. So the distance in x is 2 and the distance in y is the difference between f at x plus h here and f of x here. When I take the limit as h goes to 0, what I'm doing is bringing that second point back until it gets closer and closer and closer and closer and closer and closer to the first point, and eventually when h gets infinitesimally small, the slope of the secant line becomes arbitrarily close to the actual rate of change of the curve at that point, the instantaneous rate of change, which gives me also the slope of the tangent line. So let's use this definition to once and for all figure out what the derivative of the function f of x equals ax plus b is. So suppose that we have this linear function representing the line with slope a and y-intercept b. If I apply my definition, I take the limit as h goes to 0 of f of x plus h minus f of x over h. Well, what is f of x plus h? I replace every x with x plus h. So here's a times x plus h plus b. That entire expression here is f of x plus h. And then I subtract f of x. So what is f of x? It's ax plus b. Now I do simple algebra, distribute the a and distribute the negative sign, and I get that this is exactly the same as the limit as h goes to 0 of this expression. ax plus ah plus b minus ax minus b. And you'll notice that ax minus ax is 0, so that those two terms cancel, and b minus b is 0, so those two terms cancel. The only thing left is this is identical then to the limit as h goes to 0 of ah over h. Clearly h is a factor in the numerator and denominator, and because I have the limit contract, which says plug in values very, very close to 0, but never 0, I'm allowed to cancel. So the limit of this expression, ah over h, is identical to the limit as h goes to 0 of a, but that's a constant. So the answer is the constant, and that's precisely the slope of the line as we would expect, because that's what the derivative tells us is the slope at a point. This derivative says on a line the slope is the same everywhere. It's the multiplier of x. But notice also this implies the derivative of a constant is 0, because if I let a be 0, everything still works here, and I get 0 for the result. And that makes sense because how fast do constants change? The rate of change of a constant is 0. So we can use this rule we just derived to compute the limit or the derivative of this linear function 14x plus 11 without any work. We know by what we proved in the general case that the derivative is 14, so we don't need to use the limit definition for lines anymore. We've proved it once and for all that the derivative is just the slope, the multiplier of x. Let's see if we can make more ground. How about the derivative of x squared? Well, we'll use the definition of the derivative to prove that the derivative of x squared is 2x. Let f of x be x squared, then by definition the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. Well, how do I plug in x plus h to this function? Well, it squares its input, so f of x plus h is x plus h squared. And then minus f of x is minus x squared over h. Now I do algebra. I expand x plus h squared, which gives me x squared plus 2xh plus h squared. You can check that by foiling if you like, and then minus x squared. Notice again the x squared and minus x squared subtract to 0. They cancel out, and everything else has an h in it, as will be necessary to cancel. So we take the limit as h goes to 0 of 2xh plus h squared. That's what's left. But notice I can factor out the h, and I should always factor before canceling. So this is the same as the limit as h goes to 0 of h times 2x plus h over h. And now, under the protection of the limit, I can cancel these two. And I end up with the limit as h goes to 0 of 2x plus h. Well, that's a polynomial. So I simply plug in h equals 0 to take the limit. So this limit is 2x plus 0, or 2x. So if f of x is x squared, then f prime is 2x. And we've solved that once and for all. We'll never need to use the limit definition to determine the derivative of the function f of x equals x squared again. We've proven it's 2x. Let's try it one more time. How about the derivative of x cubed? Well, if f of x is x cubed, then the derivative of f of x, the rate of change of f with respect to x, is the limit as h goes to 0 of f of x plus h. Well, what does f do? It cubes the input, so this is x plus h cubed, minus f of x, which is x cubed, over h. Now we've got a little more work to do. We need to expand the cubic. Well, how do we do that? Well, by definition, x plus h cubed is x plus h times x plus h squared. So we can do this part first, and we know how to do that. That's x squared plus 2xh plus h squared. And now we have to distribute. Notice I can't FOIL anymore when I have three terms. What I'll do is I'll multiply every term in the second expression by x, and then multiply through by h and add them all up. So if I distribute the x, I get x cubed plus 2x squared h plus x h squared, and then I distribute the h through this second term. I get x squared h plus 2x h squared plus h cubed. And now I can pull these all together. So x plus h cubed is x squared plus 3x squared h. One of them is here, the other one's over here, plus 3x h squared. One of them is here, and the other one is there, and finally h cubed. So now I can use this in my limit definition. So this limit, the original limit, is the limit as h goes to 0 of this whole thing, x cubed plus 3x squared h plus 3xh squared plus h squared minus f of x. And again, the x cubes will cancel out this time. X cubed minus x cubed is 0. And every other term has an h in it, so we'll factor out the h. And this is the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared. And notice that every term in this expression has an h in it except for the first, after I factored out the h, right? So only this term had a single h in it. This one had an h squared. So when I factor out the h, I just get h. This was h cubed, and I factor out the h, I get h squared. So now I can cancel the factored term under the protection of the limit, and this is the limit as h goes to 0 of 3x squared plus 3xh plus h squared. Well, all the terms with h in them are going to go to 0 because now this looks like a polynomial. I just plug in h equals 0, and the first term stays, the other terms go to 0, and the answer is 3x squared. So we've proven if f of x is x cubed, then its derivative is 3x squared, and we never have to use the limit definition again to prove that. Well, this ends the first part of our video. The second part will try to go further and prove the derivative of a polynomial in general.